Okay. Well, thanks, Jimmy, for the introduction and for the invitation. It's great to be here at U Chicago. So I'm going to tell you today about 3 papers that I've written recently. These 2 with Cliff Chung at Caltech, the third one with Juan Maldacena at the IAS. Though the talk will be mostly focused on the most recent paper with Cliff, and the goal here is to bootstrap string theory, or at least string theoretic amplitudes from first principles, by which I mean I'll hand you some basic physics principles plus the spectrum of states and try and get from that alone dynamics. And what we'll find is, remarkably, the famous structures of stringy amplitudes emerge very naturally. And so we'll understand where the famous ratios of gamma functions come from, but we'll also find a whole slew of other interesting and compelling objects that beg for analysis. And so it's a sort of a really exciting set of ideas, I think. Just to kind of put this in context, this is now not working.
Okay. You might have to click again on the PDF.
Okay,
yeah,
there we go.
Then it's
so I work across kind of a broad range of fields in theoretical physics, and this talk will be mostly occupying this corner of parameter space, but a lot of what I do is kind of amplitudes adjacent in some way and kind of bridging IR and UV physics. So a few words of introduction, just so we're all on the same page for string theory amplitudes before we get into this. The bootstrap method for discovering new physics is this beautiful set of ideas that goes back to the 1960s. And the idea is to reject kind of geometry and high-minded thought experiments and instead ask the right math question about the S matrix, and you land rather uniquely on famous theories like Yang-Mills and GR. So for example, you get the universal coupling of gravity almost for free by thinking about consistent ways to have a massless spin 2 amplitude. So see, for example, Cliff's notes here for the so-called elevator-free derivation of GR. But interestingly, the analogous question for string theory, the analogous set of ideas, has not been formulated. We would like to understand what is the math question to which string theory amplitudes are the answer. And the ultimate goal is, of course, to understand, is string theory in some sense unique? We have many good reasons to believe that string theory in some form is the theory of nature. It has lots and lots of successes that I don't need to outline here, but it hasn't been proven to be absolutely unique, and it would be desirable to do that. So in order to understand that, let's ask ourselves, what is it that string amplitudes do? So the advertisement is, of course, that they unify general relativity and quantum field theory by taming the ugly trans-Planckian pathologies associated with graviton scattering. And more pragmatically, the way in which string amplitudes do this is by introducing a bunch of new degrees of freedom. That in and of itself isn't so exotic. For example, in order to tame WW scattering, one introduces new degrees of freedom, namely the Higgs. But the kinds of degrees of freedom that string theory adds are of a different nature. They're massive higher spin states. And massive higher spin states are problematic in general. If you take a quantum field theory and add a single massive higher spin state, your amplitudes get worse. You have extra powers of momenta in the propagator numerator that make the amplitudes blow up even worse. The way string theory gets around this is by adding an infinite number of massive higher spin states where all the pathologies kind of cancel as you go up the ladder. So see, for example, the paper, the famous Camaño, Edelstein, Maldacena, and Cheboidev paper for other discussion on massive higher spins. So the famous amplitude that string theory gives us for consistently coupling a bunch of massive higher spins was first written down by Veneziano in 1968 when he was quite a young man. And it has this gamma gamma over gamma structure that we'll be seeing over and over in this talk. And so what we want to understand specifically is how unique is the Veneziano amplitude. Right. So the way in which we're going to ask that question specifically is by taking an arbitrary amplitude that satisfies a bunch of physical constraints, positing some particular spectrum of states exchanged at tree level with masses given by mn squared, and then sculpting out what kind of amplitude we get that satisfies all those conditions.
So just a question about the previous comment. If you had a single massive higher spin state,
Yeah.
can you show that it's bad regardless of any perturbative expansion? Or do you need something perturbative in the?
Well, so what I'm talking about right now is just perturbatively, like a massive higher spin state exchanged at tree level violates perturbative unitarity, generally worse than the original contact interaction that it's nominally supposed to be completing. Yeah, yeah. And this is incidentally why massive gravity, for example, is so difficult, and why it's had kind of decades of alternating successes and failures. Anyway, so the three constraints are all rather benign sounding, and it'll be really interesting to see how they surprisingly sculpt out lots of cool structures at the level of the amplitude. So the three constraints are just crossing symmetry, polynomial residues, and high energy boundedness. And what we'll find, as I mentioned, is that the distinctive form of string amplitudes, the gamma gamma over gamma, arises naturally, and we'll find all these other interesting structures that generalize. So let's go through these carefully. So crossing symmetry, for most of this talk, you should think about the amplitudes that I'm talking about as describing external scalars. If you want to think about gauge bosons, you can dress all the amplitudes with the canonical f to the fourth term that you see in superstring amplitudes. So there's some polarization data that you can multiply the amplitude by, and it'll turn into a gauge theory amplitude. But it's easier just to think about colored scalars. And in that case, we want an amplitude that's cyclic symmetric. So we'll just have crossing symmetry when you swap S and T. At the very end of the talk, we'll talk about fully Bose-symmetric amplitudes, so some attempt to generalize gravitational amplitudes in string theory. That will turn out to be much harder. Graviton amplitudes are in some sense more brittle than the Veneziano amplitude. So this is why I just mentioned you can turn all these scalar amplitudes into gauge theory and gravitons by dressing them with external polarizations. So the next constraint will be polynomial residues. So on each of the poles, the residue on any of the poles at mass mn squared will be required to be a polynomial in T. And what that means is that we're exchanging finite numbers of spins. So on any pole, we don't have an infinite number of states, just a finite number of states being exchanged. And that's, in some sense, locality. If you have an infinite number of partial waves being exchanged, it's though you're kind of exchanging a cat, some big fluffy object that has support on all its partial waves. So specifically, we're going to assume that the spins run from 0 to n, just like in string theory. Yeah.
I was wondering if, like, about your comment on like the support, like if I have like the amplitude drying off fast enough for the higher spin ones, that seems naively okay, but somehow.
No, yeah. So when you add a higher spin state, its propagator, a massive higher spin propagator has Lorentz indices in it. So it's like 1 over p squared times some objects that aren't just built out of eta mu nu, but are built out of p mu and p nu. And so those extra powers of momenta in the numerator, as you make this higher and higher spin, you have more and more powers of p in the numerator. And no matter how weakly coupled that higher spin state is, it's generally bad. So the only hope of making it okay is adding an infinite tower of these guys and canceling the divergences as you go. And that's what will happen. But right now, I'm just saying I want some finite number of spins running from 0 to n. And we can consider more general polynomials, more on that later in the talk. But even for now, even with this fairly restrictive assumption, we'll find there's lots of interesting things to say. Non-polynomial residues have been of interest lately. They turn out to live on the corners of the EFT-hedron. And they're also of interest in terms of UV completing graviton amplitudes, but I won't say anything more about locality violating amplitudes in this one. So the final assumption is indeed high energy boundedness. So we're going to assume just by fiat that the amplitude dies off to 0 in the Regge limit of large S and fixed T. Now that sounds like a fairly strong requirement, but it's actually not. if you dress our amplitude with the f to the fourth or r to the fourth, you can think about this requirement as just the usual Reggie boundedness, Reggie scaling, that you want the amplitude to go like less than s squared in the gravity case or less than s in the gauge theory case. But what this means is that there's no pole at infinity. So I can rewrite the amplitude in terms of its own dispersion relation by going and sitting on some pole at s equals s prime, and rewriting the amplitude in terms of just the imaginary part. So if I plug in the final assumption that we have just a bunch of tree-level exchanges, we now get dual resonance for free. And this is what string theory amplitudes were originally famous for. This is why Veneziano wrote down his amplitude in the first place before anyone understood it was a theory of strings. He just wanted an amplitude that you could write in terms of S-channel exchanges alone, and where that T dependence in the numerator magically resums into T-channel exchanges with S in the numerator. So what we're in effect asking is, what is the set of functions of two variables that are crossing symmetric and dual resonant, which surprisingly mathematicians haven't answered yet. Right, so okay, just a little bit of caveats. This sum converges for either T below threshold or as a residue statement on the pole. And so what we'll be doing is we'll be writing down this ansatz and trying to enforce crossing by figuring out what are the set of polynomials we should use for the residues. Now, as I mentioned, dual resonance is really kind of the hallmark of stringy amplitudes. And the reason that string theory amplitudes satisfy dual resonance is obvious from the worldsheet perspective, in that you can deform an S-channel worldsheet into a T-channel looking worldsheet in a way that you can't do in quantum field theory. Right. Okay, so now those are the physical assumptions. Now to actually implement this program, we have to assume some spectrum. What's the set of mn squareds that we're going to answer this question for? And first, let's try and be as close to string theory as possible and ask this question for m squared equals n. So just an integer spectrum. Okay. So if we implement crossing symmetry in the dual resonant ansatz, we have a two-variable problem in two complex variables. And to first approximation, nobody likes too complex analysis, too complex variable analysis. So what we're going to do is going to turn it into a single variable problem by going to special kinematics. We'll choose t equals s minus some integer, some arbitrary integer that we can pick, and impose crossing just for those special kinematics and hope that we get something that's crossing symmetric at general kinematics. This sounds very ad hoc, which it is, but it will turn out to work. So crossing now just becomes this much more restrictive statement. And I can rearrange the sums into an infinite sum from k to infinity on the left-hand side, and some finite sum from 0 to k minus 1 on the right-hand side. So the thing to notice is that on the right-hand side, we have a finite number of terms with no poles at s equals an integer less than or equal to k. So we can demand the vanishing of the poles on the left-hand side, and we get a set of constraints on the polynomials. If you evaluate the nth polynomial at n minus k, it has to equal the value of the n minus kth polynomial at n for all k between 1 and n. Now there's a bunch of caveats that I should mention. Strictly speaking, this condition, though inspired by crossing symmetry, is neither necessary nor sufficient for crossing in general. It's not sufficient, clearly, because we chose special kinematics. So one could imagine that crossing is satisfied on this constraint, but not away from it. It's not necessary, in addition, because the S-channel representation, that dual resonance representation of the amplitude, was true for t below threshold for generic t, but now we're taking t on an integer, so things could break. Nonetheless, we will find this was all justified in the end, because all the subsequent examples I build using this constraint will have all of these sums I've written down satisfied and converge. So you can sort of take this as a crossing inspired constraint, and we'll use it to see what we can get from it. Yeah.
Is there a way to like write a differential equation to guarantee that like if you agree at the special kinematics, at least locally it will be crossing symmetric?
There would be if you could find the justification for why these sums will necessarily converge at integer t.
I see.
Yeah.
Because it would be like both could be infinity and then it would just break.
Yeah, right. All right, so we have n conditions, but we have n plus 1 free parameters in our polynomial because we have powers of t going from 0 to n. So we can find the general solution. I'll write lambda m comma m as just lambda m for brevity. Also for brevity, instead of writing gamma functions everywhere, I'll just write factorials. But you can imagine that the factorial is a function of any real or complex number. So that shouldn't be too confusing. And we find this general solution. So we have a bunch of free parameters. And what we find, in fact, is that if you take this as your set of polynomials and you plug in arbitrary lambda m's such that the sum converges, you get a dual resonant crossing symmetric amplitude. You can check numerically. So we have an infinite parameter generalization of string amplitudes. Now, some kind of silly choices of lambda m will make the sums not converge. For example, if you chose lambda 0 equals 1 and all the other lambda m 0, it's not going to converge. Roughly speaking, you need lambda m to fall off as of order 1 over m factorial to get this to converge. You can test that numerically. So what we want to do is choose some basis of choices of the sequence of lambda m's that roughly has that fall off and see if we can resum the whole thing analytically. But indeed, there's lots of fun numerical bootstrap problems you can ask with this as well. So this is why I just said we have this new infinite parameter family of dual resonant amplitudes. So let's see how we get string theory out of this. We choose, in some sense, a very simple choice of the lambda m's. We choose lambda m equals 1 over m factorial. One can use the van der Mond identity then to rewrite the residue, this general solution for the residue. And it just becomes t plus n factorial over t factorial n factorial, which are indeed the residues of the Veneziano amplitude. And so we can plug this in to our dual resonance ansatz. We'll use the definition of the Pochhammer symbol. So this also goes by the name rising factorial. So it's really unfortunate notation that it's a subscript, even though it's a rising factorial, but mathematicians, you know. And we'll also use the definition of the hypergeometric function, which will now appear all over this talk, so you've been warned. And finally, we'll use what's called the Gauss summation theorem to rewrite this in terms of the famous gamma gamma over gamma Veneziano form. So indeed, we've rederived the Veneziano amplitude, and we've seen how it just naturally arises from our physical constraints and just the choice of spectrum. Great. So now let's try and be more general. I said to get the sum to converge, lambda m has to roughly decrease like 1 over m factorial. A natural basis of objects that do that would be lambda m equals 1 over m plus constant factorial. So let's choose that. Lambda m equals r factorial over m plus r factorial for r any real number. So for that case, the residues also resum beautifully. And now I'm going to define for you the generalized hypergeometric function. So it's just a bunch of Pochhammers in the numerator divided by a bunch of Pochhammers in the denominator times that should be z to the k over k factorial. Okay, in that case, this amplitude becomes some 3f2, which isn't particularly nice looking. It certainly doesn't look crossing symmetric. But we can use some identities. We can use what's called a Thome transformation, named for a 19th century German mathematician, to rewrite the amplitude in manifestly crossing invariant form. So what we have is we have the Veneziano amplitude times some function that has manifest crossing symmetry. It's symmetric on S and T everywhere. And R is just some parameter. So I'll call this the hypergeometric amplitude throughout this talk, and it's just this new object that we want to study. If I send r to 0, I get back the string amplitude. This whole hypergeometric factor becomes 1 in the r equals 0 limit. So okay, let's study this in more detail. One can write it as some infinite sum over some of these generalized amplitudes I derived back in October that I'll mention later. And it's reminiscent of a string-inspired onslots posited by David Gross in 1969. But here, rather than write it down by fiat, we've derived it again from first principles. And interestingly, let's go to the special case of r equals a positive integer, where everything simplifies. In that case, you can think of it as a Veneziano-like amplitude with shifted arguments, plus a ratio of polynomials. So this looks worrisome a priori because there are a bunch of spurious poles at negative integers, but they're there on both sides of this and they cancel between the terms to give you exactly the same poles as string theory. I should emphasize, this set of amplitudes, remember, has exactly the same states as string theory. If I draw the Chu-Frauchi plot of m squared versus j, it's exactly m squared equals n spin from 0 to n. So all that's changed is not the set of states, but the dynamics. And remarkably, there's an alternate set of dynamics that still enjoys the dual resonance miracle that strings do. Oh, I've skipped ahead. Okay. So, right, another thing we should do is look at the EFT expansion. So what does this amplitude look like at low energies? So let me define the harmonic numbers and some power series of the harmonic numbers. These H and MKs have a special name in the math literature. They're called finite multiple zeta star values in the math literature for somewhat inscrutable reasons. But I should add, this is the correct EFT expansion for integer r, but it all uniquely analytically continues to arbitrary real r. And the thing to notice is that at low energies, it looks just like you expect, some cubic theory with 1 over s plus 1 over t. And then turning on this r parameter adds a constant term that wasn't there in the original string amplitude. And that actually breaks supersymmetry if you want to think about this as some gauge theory amplitude. The other cool thing about this is it exhibits uniform transcendentality. So there's a way of scoring the degree of transcendentality of a given function. Mandelstam's count as -1, each factor of pi counts as 1, zeta of n counts as n, etc. You can look up the rules in this paper. And this amplitude exhibits uniform transcendentality, just like string amplitudes. So now what about unitarity? I haven't put in unitarity by fiat. That's something one has to kind of check ex post facto. That's also the case for the Veneziano amplitude. Writing the gamma gamma over gamma, it's not obvious that all the partial waves are positive. One can check that, and indeed they are. And for a long time in string theory, the only way of proving that for Veneziano was in a roundabout way via the stringy no-ghost theorem. As of about 1.5 years ago, Nima has shown us why this is true for Veneziano analytically, but it would be interesting to do that for these new hypergeometric amplitudes. But for now, let's just check on a computer. So I'll do this more generally later, but as a preview, let's look at massless external particles in 4 dimensions. So I'm going to just take that residue and expand it in Legendre polynomials. And unitarity will require that all of the A and L's are positive, or at least non-negative. And the reason is that they're just the coupling squared of the spin L intermediate state on the nth massive pole. So we can check that. You can, after a long calculation, you can read off what the partial waves are in terms of Stirling numbers. And you can plot it, and it's quite beautiful. So this is Veneziano, and it's all positive everywhere. And then for different values of r, it remains positive. So that's a good check that what we've done still has a chance of being a physical theory. The next thing we want to understand about these new hypergeometric amplitudes is their UV behavior. Are they well behaved at high energies? So we can look at the hard scattering limits. So S and T both large and T over S fixed. And then the hypergeometric amplitude exhibits the following scaling. You have this exponential term. And so there's this universal S plus T log S plus T minus S log S minus T log T, plus some power law term, R over ST. And which dominates depends on whether you're in the physical or unphysical regime. In the physical regime, one has B negative, and so the amplitude falls off as a power law, R over ST, unless R equals 0, in which case you get the famous exponential decay of string theory. On the other hand, in the unphysical T positive region, you have B positive, and you get the universal scaling predicted by Simone Karen-Huo and company. So good, so we satisfy the theorem that they proposed. So now what about the Reggie limit? At large S and fixed T, one has indeed that S to the T behavior that you see in string theory, plus some subleading term R over 1 plus T times S. And again, the spurious poles cancel between the two terms. Right. So now we don't yet know what are the underlying dynamics of this model. That's something that we really want to understand. But to kind of inch towards that, it turns out that there might be some worldsheet-like interpretation of these rather exotic amplitudes. So remarkably, the hypergeometric amplitude can be written in this double integral form. And this reminded us a lot of the Kobe-Nielsen form for the Veneziano amplitude. So you can write the gamma gamma over gamma as a single integral. Now, when you do that integral in string theory, a priori you have 4 parameters to integrate over, but you can fix 3 of them using modular invariance, and then you just have 1 to integrate over. So the fact that we have 2 variables to integrate over suggests that modular invariance is working differently in whatever underlying theory this is describing. But interestingly, you can actually understand this in terms of the 5-point string amplitude. So if you take the 5-point Veneziano amplitude, which is given here, it's indeed a double integral. And the minimal basis of Mandelstam's are just the cyclic ones, S12, S23, S34, S45, and S51. And if you fix special kinematics, so I fix S34 and S51 to just numbers, to -1, and S45 to -R, and I view S12 as the 4-point S and S23 as the 4-point T, I get exactly our hypergeometric amplitude. So it's as though we're taking the 5-point string, fixing some weird kinematics. You cannot interpret this as fixing any of the PIs to special values. It's something more exotic than that. And you get back an amplitude that's miraculously a sensible 4-point amplitude, and that's crossing symmetric. In this picture, you now can understand why there's this factor of R living out front of our integral form of the hypergeometric amplitude. When R goes to 0, the worldsheet factorizes into a 4-point amplitude times a 3-point amplitude. And you have a 1 over R propagator from the state that's going on shell, the intermediate state. And so you need that extra factor of R to cancel the pole. That's fundamentally where that comes from. But it just falls out naturally from the math. So I mentioned that we have really an infinite space of amplitudes that are dual resonant by choosing any lambda m's that have the right overall fall-off behavior. A nice way of viewing that is by just writing some arbitrary function mu of r that's kind of the binomial transform of the lambda m's. So if I define the lambda m's as mu of r times this ratio of factorials, I get just some admixture of our r-dependent amplitudes weighted by the mu's. And that roughly parameterizes all lambda m's that fall off like 1 over m factorial. Good. So I think I'm on time here. So what we now want to do is q-deform everything. So I've given you the story for the integer spectrum, m squared equals n. But we could think about arbitrary functions, m squared equals n squared if we want to think about Kaluza-Klein, whatever. But a particularly nice choice of spectrum that has a long history that we'll talk about is the so-called q-deformed integers. So these are kind of logarithmic deformations of the integers.
So before we jump into Q definition, did space-time dimension matter at all in the prior discussion?
It didn't matter in terms of constructing the amplitude. It does matter for whether it's unitary or not. So when I showed the partial waves, that was for 4 dimensions. I'll ultimately show you what happens in d dimensions, because indeed for the Veneziano amplitude, you can read off the critical dimension from unitarity of the partial waves. And adding this r parameter will change the critical dimension in an interesting way. So we'll get to that after I go through the Q deformations. I'll kind of sculpt out the unitary space for an even bigger theory, an even bigger set of objects. Good. So as I mentioned, historically, the actual writing down of string amplitudes predates the realization that the theory was about strings at all. Lenny Susskind realized it, and others did, within roughly a year after Veneziano wrote down his amplitude. But also within roughly a year, people were writing down generalizations of the Veneziano amplitude. And a guy named Coon in 1969 wrote down a beautiful generalization of Veneziano that was then tragically forgotten by almost everybody for decades. This is the graph from Inspire of the citations, and you can see it just flatlines for decades until literally the last year and a half when we've all started getting interested in this again. And the recent surge of interest has several different sources. People have been trying to understand the unitarity of the Coon amplitude. I've been trying to find ways of realizing it in string theory with Juan, and Cliff and I and some guys at UCLA have been kind of generalizing it and better understanding its construction. So here it is. It can be written in terms of this beautiful infinite product, where here sigma and tau are just shifted and rescaled Mandelstam variables. We'll talk about those later. And the important thing is that q is some parameter between 0 and 1. This goes back to string amplitudes when q goes to 1, and you get an accumulation point in the spectrum as q to the n goes to 0 as n goes to infinity. So it's kind of like hydrogen. You have a bunch of states that get closer and closer together, and then there's some ionization threshold that, that the logs tell you about. Good. So now let me say a few words about the sort of theory of Q analogs in mathematics. This is a whole field of mathematics, basically deforming every function that you know and love by some new parameter Q. So it starts off by Q deforming the integers, which is written as n sub q with square brackets. And you can think about it as just 1 plus q squared all the way up to q to the n minus 1. And what it does is you can see here, you have the integers as q goes to 1. And then for q less than 1, you have some accumulation point given by the red curve. From the q-deformed integers, you can define a q-Pochhammer symbol, which is the q deformation of the usual Pochhammer symbol. And you get factorials, binomials, q-gamma functions, etc. And unfortunately or not, there exists q-hypergeometric series that have bizarre notation. Instead of writing it with f's, like I would have, it's written with these phi's. And you can see they reduce to the usual hypergeometric series when q goes to 1 in this way. So there's some exponential behavior that becomes a linear behavior in the hypergeometric. So this will all show up, all these structures will show up henceforth. I'll just flash them up here for now. Okay, so what we're going to do is we're going to bootstrap an amplitude whose spectrum is given by the q-deformed integers. This is not how Coon originally built his amplitude in 1969. He did not build it in a very physical way via bootstrapping. He instead asked a much more aesthetic question. He asked, what is the set of amplitudes that can be written in that beautiful infinite product form? Because for him, the most important fact about Veneziano is that it can be written as an infinite product. Instead, we'll be physicists more, and we'll just say, this is our spectrum. Let's build an object that's dual resonant and see what we get. So let's define some new auxiliary variables inspired by the q-deformed integers. So sigma and tau are just the q deformations of s and t. And let's assume a dual resonant ansatz. So we have a bunch of poles in the s channel at the q-deformed integers, and we have some polynomials in t. And we want to figure out what are the polynomials in t, just like before. So we can run through the same sort of argument. We can choose special kinematics, impose crossing, and we get a q generalized residue constraint, which is just the natural generalization of what we had before. So we can find the general solution. And again, we have a bunch of free parameters, lambda m, that we have to pick and see if we can resum all of this analytically. Incidentally, I should add, so even though this talk is very analytic, this is unusual for the Bootstrap program. Normally, when you bootstrap, everything is numerical. And when we originally did this for the integers, we actually did it numerically using Mathematica's linear optimization functionality. And then we started spotting patterns, and we realized we can go back and do the whole thing analytically. So there's a lot to play with here, even if you like numerics rather than analytics. All right, so we have this general solution for the R's. Let's plug it back into our dual resonant ansatz and see if we get something sensible. So if we choose the lambda m's in such a way that it generalizes the 1 over m factorial of string theory and use the q-deformed van der Waals identity, the residues resum nicely. And we can try plugging it into the dual resonant ansatz, but a catastrophe occurs. The amplitude doesn't converge, crossing fails, nothing works. So what's going on? Well, there's additional freedom, which is that I've written down an amplitude ansatz in terms of a bunch of poles, but you can also add contact terms, right? Terms that are invisible to the poles. Equivalently, I can multiply any of the numerators in the ansatz by something that goes to 1 on the pole without changing any of the story. So let's write down the simplest conceivable function that goes to 1 on the pole, q to the tau times sigma minus n, okay? So we can do that, and then everything works. The amplitude converges, the sum turns out into q to the sigma tau times gamma gamma over gamma, except these are q-deformed gamma functions. And this is exactly the Coon amplitude. I claim, and you can show that the infinite product I wrote down before can be rewritten precisely like this. So we understand naturally how the Coon amplitude arises. And I just want to show you what the Chu-Frauchi plot looks like for the Coon amplitude. So here, the navy dots are string theory, which I drew previously. And then when you dial down Q from 1, you, rather than have the spectrum march off to infinity, you have some finite accumulation point shown here for different values of Q. Now, a few comments about the physical attributes of the Coon amplitude. At high energies, you get sort of strange behavior. You get that the amplitude looks like a double log S log T. So we have this kind of weird branch cut with this double log structure. But we shouldn't be too worried about this because last summer in the string constructions that Juan and I found, I'll show you more about these later, but we found that indeed string amplitudes of the sorts we constructed also have this double log form at high energy. So this has to be physically healthy. And again, the accumulation point suggests some sort of ionization process. But recent work by Christian Jepsen at Stony Brook has shown that even though all the poles are unitary and the branch cuts unitary asymptotically, where you get the double log, exponentially close to the threshold, the branch cut exhibits a failure of unitarity in the Coon amplitude. And so that suggests something has to be done to actually save the Coon amplitude and make it unitary again. But I would add that let me go back to this. The actual log structure in the Coon amplitude that sits in this Q to the sigma tau prefactor was fairly ad hoc. Coon and company added it later as a way to cure some non-polynomiality of the residues. Basically, they wrote it down as the simplest possible function that looks like tau to the n on the pole. We added it as the simplest possible object that we could multiply each of the numerators by that goes to 1 on the pole. So it's the simplest possible contact term. But there's a whole slew, a whole infinite class of functions that you could write down that also does that. And no one's really explored that space of objects. And I think it would be good to do so to try and see if the Coon amplitude can be cured somehow. There's almost a no-fail theorem for this process because, again, we know of string theory constructions that capture many aspects of the Coon amplitude. So something along those lines has to work if we believe that string theory is unitary, which we do.
So like these string theory examples,
yeah.
What is the reason behind, like they are also possibly non-unitary in the conventional sense of...
No, the string theory amplitudes are going to be unitary, but they don't actually match the Coon amplitude precisely. I'll show you more about them later. There are different string constructions that match one or the other or another physical attribute of the Coon amplitudes, but there's no single string construction that does all of it at once, but we kind of know what it would have to involve. Yeah, I'll show you what those constructions look like later.
Sorry.
Yeah.
Conversely, is it possible to choose a tracing factor such that it produce your string amplitude with the brain that has this?
Yeah, I mean that's what I'm saying. I mean we don't know what the string amplitude with the D brain is in general. Like we computed it in different limits for different setups. But yeah, that's what I'm saying. That there should be some choice of prefactor that corresponds to one of these string theory constructions, and that's guaranteed to be unitary because string theory is unitary. So now what I want to do is I want to generalize the hypergeometric story in this Q direction.
Sorry, just.
Yeah.
So your statement is that like the string theory constructions in some limit seems like Coon amplitude.
Yeah. So okay, I'll give you a preview of what they do now. So take anti-de Sitter space. Where's the chart? There it is. Okay. So if you take ADS and here's the boundary, and you put in a D brane at some fixed bulk depth, and then you attach open strings to it. So let me draw it like this. So if you attach open strings to it and you scatter them, you find, using the standard stringy techniques for computing the amplitude at high energies, that that you get this log A goes like minus log S log B. And actually the Q parameter corresponds to a ratio of alpha prime to the ADS radius.
So like about this, just this amplitude, not even the high energy limit, like
Yeah.
suppose you're able to compute it like, exactly like.
Yeah. Then it might indeed be the Coon amplitude. I mean, another reason we think that it is we can write down constructions that involve just a single string that actually have an accumulation point. So if you take a single string, attach it like this, and spin it, you can semi-classically quantize that system, and you find that there's an accumulation point, that you go out to infinite energy but finite energy but infinite angular momentum.
And those amplitudes, you explicitly see them to be unitary.
No, well, they're guaranteed to be unitary because they're stringy, right? You know the underlying dynamics is some consistent theory.
I'm just.
We don't know how to write down these amplitudes at general kinematics. We can write down the spectrum of states, and we can write down the amplitude at high energies, but it's going to be guaranteed to be unitary by like stringy no-go.
I meant to say that like maybe my question was that like, do the usual notions of unitarity this thing, because like you have some extended objects and you're scattering stuff.
Yeah, but the usual notions of unitarity will apply. The usual notions of locality don't apply. But unitarity is again, it's basically a statement about linear algebra, right?
I mean, string scatterings of branes, like you explicitly violate Lorentz invariance, right? I mean, there is a specific.
Well, no, I mean you still have Lorentz invariance within
the
brain.
I see.
Yeah.
So some lower dimensional unitarity is okay.
Yeah, you should think of it as some theory of objects in the brain. We have some bulk description, but if you're just computing S matrices, you don't care about that. Right. Good. So, okay, yeah, I was going to say, so before we get into that more, I want to tell you how the q-deformation story all generalizes in this for these hypergeometric amplitudes. So we'll write down a more general choice of the lambda m's, and we can rewrite. We find the residue in closed form, and then using the q-deformed version of the Thome transformation, we get a new class of crossing symmetric dual resonant q-deformed amplitudes that generalize everything we've written down before. So it's the Coon amplitude times a 3 phi 2 times a q hypergeometric. And so you can think about some space in QR space, right? The Veneziano amplitude string theory lives at the purple dot. The hypergeometric amplitude, the 3F2, is the orange line. The Coon amplitude is the blue line, and now we've filled out the full space in green. And now what we should do is we should check if this full space of objects is unitary. So we can go back and read off the partial waves. Let's be more general now. So before I was considering massless external states, but I can even allow the external states to have mass by sending s to s minus m naught squared and t to t minus m naught squared. So I can even allow for example, the bosonic string, where Veneziano describes tachyon scattering. So I can again expand in Gegenbauer polynomials. So I can do this in d dimensions and impose partial wave unitarity. And so you get some ugly expression for the partial waves, but you can go and check this to however many partial waves you like. And if it's going to fail numerically, it fails within the first few partial waves. There are no examples we know of where it's unitary for like 10 or 15 partial waves, or from n equals 0 to 15 and then fails above that. So, okay, so I'm going to show you various slices through this space. So let's choose q equals 1 first. So this is just the 3f2 amplitude. Nothing is q-deformed right now. This is the integer spectrum, but we're going to plot in r versus m naught squared, okay? So the superstring is that it lives at the red dot. R equals 0, m naught squared equals 0. And here, everything above a given line is what's allowed. Everything in white is forbidden, and different lines correspond to different numbers of dimensions. So the dashed line here is the 10-dimensional line. So indeed, the superstring lives on the boundary of the 10-dimensional unitarity line. The orange dot is the bosonic string. And dashed line is d equals 26. So the bosonic string is interesting in that it lives at a corner of this parameter space. So r is as low as possible for the bosonic string at 0. The other interesting point is this purple dot, for which the critical dimension turns out to be exactly an integer. So from the point of view of unitarity, it's just as compelling as string theory, but it's not a string theory. It has massless external states, and it has critical dimension equal to 5, precisely 5, and it has r as low as possible at -0.5. So it would be really interesting to understand what that theory is. It's a pretty compelling object. Another slice through the parameter space that's interesting is if I choose massless external states and then just plot in Q and R space, right? So here,
The previous case could not be impacted by string theory.
well, it might be, because again, remember, all the R-deformed theories can be gotten from taking the 5-point string and choosing some special kinematics and turning it into a 4-point amplitude. So we don't yet really know what these theories are. Right. So again, above the line is allowed, and we see that as we go to higher and higher dimensions, less and less of the parameter space is allowed. But here in the dark teal, that space is unitary in d equals infinity. So I can put this all together and show you the full 3-dimensional space of q, r, and m naught squared in various dimensions. So here's the 4-dimensional chunk of parameter space that's permitted, d equals 10, and d equals 26. And you can sort of see how the plots I showed before fit together on the faces of this object.
Is there any nice story in d equals 11?
Not that I know of. I mean, even for the Veneziano amplitude, nothing particularly special happens in d equals 11. It's d equals 10 and 26. Yeah. No, the only other special point that I found in the space was the d equals 5 extreme value of r point that I showed earlier. We can understand lots of these bounds analytically. You can show that m naught squared is upper bounded by 1/3. And you can show that there's some minimal analytic lower bound on the R parameter. And this is just what I mentioned about the critical dimension, but we want to follow up on that in future work. So I'll briefly mention this story about accumulation points in string theory and how you can arrive at the Coon amplitude and indeed generalizations of it from kind of aesthetic means by thinking about infinite products. So here's some of the constructions that I looked at with Juan. We looked at the spinning string attached to the D-brane, and here you can see numerical data in red and various analytic fits in green and blue. And you can see there's an accumulation point in energy at large angular momentum. And what's happening is that it's gravitational redshift that's making this happen. As you make the angular momentum larger and larger, the endpoints of the string fly apart, and the string probes deeper and deeper into the bulk, where it contributes very little to the energy. Most of the energy is concentrated at the endpoints, and eventually things just saturate. Now, that's very similar to what happens in the Coon amplitude, but numerically, the accumulation point is approached as a power law here for the string, whereas the Coon amplitude approaches the accumulation point exponentially. So that's not so good. We can find an exponential accumulation point if instead of just spinning the string, if we stretch it, if I take the two endpoints close together and I stretch the string and semi-classically quantize that system, there's again an accumulation point corresponding to the string going all the way to rho equals infinity at the Poincare horizon. And you find that the accumulation point is approached exponentially in that case. So that's good, but nothing is spinning. That's like the accumulation point all along the j equals 0 line in the Q-Fauci plot. So to actually get the full Coon amplitude, one needs some sort of stretched and spinning string system. And we didn't investigate that, but that would be a great future project to try and really hit the nail on the head and get all the features of the Coon amplitude.
So what's the holographic tool to this when the AES is made out of these deep brains? Like, is there some kind of Coulomb branch?
Well, so AES here isn't really, we only are putting in one D brain in ADS.
Right, so you have a probe in there.
Yeah, yeah,
And then you're scattering on that probe.
yeah, that's right.
It should still have some kind of holographic.
It should have some we didn't think about that, but yeah, I mean, there should be some nice holographic interpretation. Yeah, no, we didn't think about that. So now I want to go back to the way the Coon amplitude was originally constructed and tell you a little bit more about that. So again, as I mentioned, Coon started out by thinking about some infinite product ansatz looking like this with arbitrary functions f, g, and h. And the idea was he wanted to build an amplitude that again has a finite number of spins on each pole. So the way he wanted to accomplish that is when you sit on the pole at sigma equals f of n, you want n factors of the numerator to come out and give you your polynomial in t, and the rest of the t dependents in the remaining infinite product to fully cancel. So there's some cancellation, some like spin truncation constraint that happens. So that ends up being some consistency condition among f, g, and h. Now, what we did on this paper in the fall is we thought about, well, okay, rather than having n factors of the infinite product peel off and cancel, what if it's p of n for some arbitrary polynomial? That is, what if the spins don't go from 0 to n, go from 0 to p of n? It turns out you can prove that the only possibility is for p of n to equal n plus alpha, for alpha equals some fixed constant. So you have to have a number of spins that's linear in the pole number if you want some infinite product. Another interesting fact about this is that if you want that final infinite product to all cancel and to be left with some finite number of spins, again, as I said, you have some consistency condition among f, g, and h. If you promote n to a real number and turn that into a differential equation, it can be rearranged beautifully into just the statement that the Schwarzian derivative of f is a constant. No idea why a Schwarzian appears here, but it's really cool because it tells you that we like Schwarzians. We know what the general solution is. It's a plus b q to the n over c plus d q to the n. And you can fix a, b, c, and d by choosing the endpoint and choosing the overall units. And what you get uniquely is that mn squared equals the q-deformed integers up to some shift and mass scale. So that's great. That falls out naturally from this infinite product structure. Finally, if you allow the prefactor w, which was that log q to the log factor, if you allow that to be something more general than just what Coon wrote down, one possibility is introducing these extra factors beta and gamma. So this is a triply generalized Coon amplitude that has these extra integer parameters alpha, beta, gamma that generalize the space. And so you can think about this as generalizing the spin structure. On the kth pole, you have spins running from 0 to alpha plus beta plus 1 plus gamma times k. Right, okay, so then you can kind of sculpt out what space in this set of amplitudes is unitary. I'll plot for you what the states look like. So this is the Q-Fauci plot for Coon. So that's alpha, beta, gamma all equal to 0. Turning on alpha or beta contributes linearly to the spectrum. And then turning on gamma contributes multiplicatively to new states in the spectrum. And you can read off all the partial waves. It's sort of terrible, but you can numerically sculpt out the allowed parameter space. So these are individual partial waves, and then you sandwich them all together to get where everything is consistent. And you find that for various choices of alpha and beta, gamma ends up having to be set to 0. There's still theory space that's allowed. So that's yet another direction of generalization. We would like to take our R amplitudes and generalize them further in this direction as well. But I see I'm running out of time. So in the last few minutes, I'll tell you what happens if you try to do all this for gravity. So if we consider a fully Bose-symmetric amplitude, full STU symmetry with massless external scalars, so like scalars exchanging gravitons, we can again play the same game, write down the amplitude in terms of a dispersion relation, and assume tree level exchanges. But now, since we're Bose-symmetric, we allow exchanges in both the S and U channels. So let's assume a linear spectrum. Now I can add the 1 over STU term for free because it's trivially Bose-symmetric and dual resonant, which is good because that means I can match onto GR at low energies. Let's also assume that we have spins running from 0 up to 2 times n minus 1. Once I address this with r to the 4th, that'll be spins from 0 to 2n. So it's again matching Virasoro-Shapiro amplitudes in string theory. And what we're going to do is try and fix the kappa NMs to allow for crossing symmetry. So because we're doing a fully Bose-symmetric problem, we have additional constraints. We have to enforce ST crossing symmetry on both the S channel poles and the U channel poles. So we have to satisfy all these constraints simultaneously. So we have some general solution given here. It amusingly has some kind of a double copy-like structure. You can see something that looks almost like a product of some square. But the analogous calculation with a q-deformed spectrum gives no solutions. It's not possible to q-deform Virasoro-Shapiro, it turns out. But let's see if there are choices among the kappa m's that allow us to resum this analytically. So with the benefit of hindsight, let's choose kappa m as shown here, in which case the amplitude looks like this in terms of a 4f3 hypergeometric. Again, that's kind of ugly. It's not obviously crossing symmetric. And in fact, in general, it's not crossing symmetric for arbitrary real r. But if r is an integer, you can rearrange this into something that is manifestly fully Bose-symmetric. And it generalizes the Virasoro-Shapiro amplitude. We get back string amplitudes when r equals 0. And in fact, in the EFT-hedron paper, this amplitude was anticipated, at least for the r equals 1 case. They wrote down this amplitude as a deformation of Virasoro-Shapiro when r equals 1. The one other comment I'd like to make, even though it's slightly unrelated from the rest of this talk, but it's just really cool, is that you can push the idea of dual resonance even further. So when I wrote down dual resonance for the fully Bose-symmetric problem before, I was requiring that I can rewrite the amplitude in terms of S and U channels times some residues that depend on T. But I can do even more if I allow the residues to depend on S and T. That is, if I allow for contact terms, I can rewrite the string theory graviton amplitude in terms of the S channel alone. So it's like there's a sort of triple resonance. You can write it as an S channel alone, a T channel alone, or a U channel alone, where these new ST symmetric residues satisfy literally a double copy-like relation. But this doesn't come from the double copy itself, because this involves the massive internal states. So why this is happening, what this means more generally, we don't know, but it's really kind of shocking. So I'm just about out of time. So just to wrap up, remind you what we did and what we want to do next. We found this really amazing new infinite parameter family of dual resonant amplitudes satisfying basically everything you would want physically. Reggie spectrum, UV boundedness, polynomial residues, etc. And for particular choices, we've got these beautiful hypergeometric amplitudes that we're studying now. Everything in sight q-deforms beautifully, and everything apparently remains in satisfaction of partial wave unitarity in large regions of parameter space. So this has a chance of being a real physical theory. And as we've seen, graviton amplitudes are much more brittle. There's much less room to maneuver. In future, we're pursuing multiple different directions. We want to think about dual resonance bootstraps for totally different mass spectra than just integers or q-deformed integers. But more immediately, we're pursuing higher point generalizations of these hypergeometric amplitudes. For example, starting out with 6 and 7 point Veneziano amplitudes and choosing special kinematics that reduces them to 5 and 6 point cyclic amplitudes. That's much harder because you have additional types of poles that can enter. We would also like to try double copying our hypergeometric amplitudes and see what we get gravitationally. But kind of more broadly, we want to understand what is the physical system that these new objects are describing, because they're pretty compelling. And in fact, in a sense, they should have been written down in the 60s when Veneziano wrote down his gamma gamma over gamma structure. People should have asked, what is the full set of dual resonant objects? And this is useful even for string theory. If you want to prove that string theory is somehow unique, it behooves us to try and explore all these other directions. And as we've seen from my stringy constructions with Juan and from the world sheet representation of these Veneziano or these hypergeometric amplitudes, thinking about these new objects can end up teaching us things about the original string theory that we didn't know to look for. So this kind of goes into the broader context of a lot of what I do, which is kind of combining ideas from both the UV and IR to get all sorts of interesting new physics. And outside of just this kind of stringy bootstrap, I've thought about this approach in lots of different contexts, ranging from the weak gravity conjecture to black hole physics and beyond. And so thanks very much, and I'll take any other questions.
In addition to having like the 1 over m factorial follow-up, like you could presumably dress it with like logs and so on, right?
With logs.
And that would still converge presumably.
Yeah, that would work. Yeah, rather than polynomials with logs. Yeah, so that would not be, well, it's not obvious whether that would be in our basis of our amplitudes or not. And so yeah, that's something we haven't thought about, but indeed, that should converge. Yeah.
Is there any hope to push these to strings on ADS5, meaning this spectrum, or at least in some expansion for ADS5, but it's not known how to compute amplitudes? I mean, the Virasoro-Shapiro amplitude for ADS5.
Yeah.
Is there any hope to bootstrap it from the spectrum?
I mean, yes. Yes, it's possible to, well, it's conceivable that one can bootstrap that from the spectrum. I mean, everything I've done here is really about amplitudes in flat space rather than amplitudes in curved backgrounds. If you wanted to think about this for amplitudes that really fundamentally live in curved backgrounds, the whole story would be much more complicated because you don't really have Mandelstams anymore. You have whatever representation is appropriate for that background. But yeah, one could play the same game. General backgrounds is probably hopeless. ADS is probably symmetric enough to do this. So yeah.
Sorry, in some sense, even within string theory, you would have expected as you go down in dimension, you get a massive explosion in the number of consistent S matrices right down.
Yeah.
In the tree level, right? From whatever the number of geometries that you can get from a 1 manifold, 2 manifold, 3 manifold, and then it starts getting big, right?
Yeah.
5 and 6.
Indeed, but most of those will have other spectrum, because remember, I plugged in the set of m squareds, right? If I take string theory and I compactify on whatever manifold, you not only have the m squared equals n, but you have kk states that have m squared equals n.
Spectrum of,
Yeah, so those should correspond to all sorts of other exotic choices of the sequence of m squareds.
Okay. So there's the integer spacing that you picked that was the sort of assumption that it's in some sense flat.
Yeah, exactly. Yeah.
But on the other hand, the 10D amplitudes themselves should have been M theory on the circle, at least in one case, which would have again looked like a set of KK states.
Yeah. So there should be some way of well, indeed. So okay, I can tell you what we've been finding numerically, but I mean we've been playing with adding in m squared equals n squared, adding KK states. Choosing just m squared equals n squared is with no m squared equals n asymptotics is guaranteed not to work by Simone and Company's theorem about asymptotic uniqueness of Veneziano. So somehow what we would need is some exotic sequence of m squareds to actually make this work. We haven't gotten that to work yet. We're actually focusing on the higher point story more right now, but yeah, that's something we want to come back to.
Regarding the higher point story, so like I can think of your amplitudes and take some low energy expansion. So these should correspond to some Wilson coefficients of some effective field, the R to the power 4 effective field.
Yeah, that's right.
Right. and these Wilson coefficients are now dependent on R or some generalized parameters.
Yeah,
Is there any hope of like using, like trying to study the higher point amplitudes, you'll be able to like fix these Wilson coefficients even more, even for R to the power 4?
yeah, okay, I see. Yeah, that is an approach. So you're advocating basically the EFT first approach,
Yeah.
basically,
Yeah.
look at the low energy expansion and then use that to maybe build a higher.
Like, I mean, yeah.
That's an option. Right now, what we're trying to be a bit more ambitious right now and kind of get it all in one go, where we're trying to use the world sheet at fixed kinematics input as inspiration. But yeah, if that doesn't work, we'll probably do indeed what you're saying is go back and build it from the low energy EFT description. Yeah.
I mean, the hope would be that such a bootstrap approach would uniquely fix these coefficients,
Yeah.
right? I mean,
It's not clear though whether.
yeah, for sure. I mean, that's a long way to go, but like I see.
A lot of the intuition is stringy based, but how do you know when it's really connected to a string or something more exotic?
We don't. We don't. Because the bootstrap is inherently agnostic about the origin. It's just, hand me a spectrum, hand me some set of spins, and do I get a consistent amplitude or not? We thought about actually trying to do this completely generally at 5 points, doing the full bootstrap at 5 points, but that seems honestly kind of hopelessly difficult because it's already really hard at 4 points, as you've seen this talk, and to try and do the full bootstrap in general at 5 points is probably too hard. So I think our best chance is this world sheet-esque approach, but yeah, not clear whether it'll work or not.
So for 5 points, like, so since you have thought about this, like, how does the Regge behavior work out? Because now, like, I mean, what are the constraints on Regge behavior that one would like to impose on a 5 point amplitude? Like,
Well, no. So I'm not even doing that. So I'm not building 5 point from a dispersion relation. I'm literally asking if I take the 6 point Veneziano amplitude, can I choose? So at 6 point, there are 9 different independent Mandelsams. Can I choose some subset of them to kill off all the spurious poles and to have the remaining 5 independent Mandelsams at 5 point magically cyclic invariant?
I see.
That's what we're trying to do right now.
Even that is.
And even that's hard. Yeah.
Is there a nice world sheet interpretation of like the limit you are taking to get the 4 point from the 5 point? Like some.
We don't know. I mean, the world. So the interpretation, I mean, is saying, okay, S51 equals S34 equals -1, and S45 equals -R. But what does this mean in terms of the actual underlying dynamics? Does it mean I'm like effectively taking one of the strings and gluing it to a braid or something? We don't know. But in a sense, that's the lowest hanging fruit, although that's not what we're thinking about right now, is trying to understand what on earth does that mean for the string? Is there even some interpretation of that in terms of something in position space?
If no other questions, then let's take a break.